theory of relativity. He proposed it, formulated, created it exactly 100 years ago. Now, some of you were here for the last talk also. In contrast to the arrangements last time, you can see that my seat, if not my status, has been elevated. And also, I am sitting down and giving this talk. And this is in accordance with our ancient tradition of Upanishads. I don't know whether you know, I didn't know this, but Upanishad apparently means sitting near. So in those days, all the gurus and shishyas used to sit next to each other very close and talk, discuss. I am not claiming that I am a guru, because even in those days, gurus could be younger or older than the shishyas. So I can count myself as an older shishya with all young gurus in front. Of course, with the exception of Professor Lokanathan, who chronologically is older than me. So we will start with this talk today is going to be general theory of relativity. Last time it was special theory of relativity. This time it is general theory of relativity, space-time, and gravitation. So as I said, many of you might have been here last time. So where were we last time? In space, in the patent office at Bern, and in time, the year 1905. That is when Einstein formulated his special theory of relativity, in which he proved a number of things, but the most important thing for us today, even in these days, that he showed that space and time were interdependent upon each other. They were inextricably entangled. Professor Lokanathan will teach you one of these days entanglement in quantum theory. But here space and time were entangled with each other, but they were interdependent, but there is no notion of space-time. Space was there, time was there, they were interdependent, but still space-time had to come into existence. That was done by this man, Hermann Minkowski. He was a brilliant mathematician, and he was a professor at the Federal Polytechnic Institute in Zurich, or called by everybody as simply Poly. He was a mathematics professor, and Einstein was a student in Zurich Poly between 1896 and 1900 for 4 years. So the story, or it's a historical fact, that Einstein used to cut Hermann Minkowski's mathematics class. He was not attending. In our schools they take attendance, but in the West they don't take attendance. So he was cutting the classes, so much so that apparently Minkowski referred to Einstein as that lazy dog Albert Einstein. So that was the relation between Minkowski and Einstein. But on the other hand, much later on when Einstein wrote his autobiographical notes, it's really a marvelous document, he pays tribute to Minkowski and many other teachers as the excellent teachers he had in Poly. But then Minkowski moved by 1905, when Einstein gave his theory of relativity, had moved to Göttingen, so which was the seat of physics and mathematics at that time. And there what he did was, he took relativity and created this space-time. He called it the world. You should read his original paper, it's very quaint. He called it world, but we call it space-time. Now he created blending space and time together, which was one of the most important step in not only special theory of relativity, but general theory of relativity. Now when Einstein was told that Minkowski had done this, and what was his reaction? This was in 1906 or 7 or something like that. Einstein smiled and said, now that mathematics has invaded relativity, I no longer understand that theory. So even then he was saying that, but soon enough he realized that this space-time was extremely important for his own development of general theory of relativity, that we will come to that. But to continue the story of Minkowski himself, after 1908 when he really formulated this space-time picture of special theory of relativity, he became ill with peritonitis. Peritonitis, I learned, is a fatal inflammation of the inner lining of the abdomen, which protects all the organs in the abdomen. So he died soon after, and his last words were, what a pity that I have to die in the age of relativity's development. Very tragic indeed, because we don't know if he had lived what great contributions he would have made to relativity, or maybe he would have collaborated with the lazy dog Einstein, and maybe something beautiful, something great would have come. But in any case, Einstein was going to use what he had done, space-time, as we shall see soon enough. Now, 1908, when he did this, he said, henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. That was the prophetic words indeed, because the space-time blend that was going to remain, and even today, when we want to do physics, space-time is used. Of course, it's often convenient to break them into space and time, but when we do general theory of relativity, we use space-time all the time. So let us take a look at what this space-time is. We know, all of us, ordinary three-dimensional space. Can we have the questions at the end? Is that all right? Preserve your questions, remember them, and ask me, and I don't guarantee I will answer you. That's always the disclaimer. Okay? So in the three-dimensional world, as we see, here is the picture of a room, for example. One corner is a point there, and the other point is a bulb or anything else, and the distance between the two is the and Pythagorean theorem, delta L squared equal to delta x squared plus delta y squared, etc. We know all this. And also, delta L squared is in three dimension an invariant. You could rotate the axis. If some of you have seen the movie Gold Rush with Charlie Chaplin, this thing rotates like that. The cabin when about to fall into the gorge. But the bulb is perpendicular always. Similarly, here the delta L squared is invariant whether you rotate the coordinate systems or move the coordinate system, which is called translation, it is invariant. But now here is a great thing that was done by Minkowski. He made it into 4 dimensions. You have 3 dimensions already, x, y, and z in Cartesian coordinates, and t, the time he made it into a 4th coordinate, so that we are going to live from now on in a 4-dimensional world, and this is how we did that. Take for example, here t is along the vertical direction, vertical axis, and only space x is used. You cannot show all 4 of them, impossible. Maybe one more I could have done, doesn't matter. And now here is, we used to have points in 3 dimension, now we call it in 4 dimension an event. Because event tells you where it happened and when it happened. Where is given by x and when given by t. So here are 2 events. This cowboy shoots a gun and the bullet keeps going. You see the bullets are going in time, not just in space but also in time. When you plot the coordinates, both the time coordinate and the spatial coordinate of the bullet, you see that going, and finally the second event, it hits the bottle. So therefore these events are separated in coordinates by x and in time by t. That's very important. And Minkowski, look at the simplicity of this equation. You had only the 3 of them. The last 3 times now, he adds c squared delta t squared. C is the velocity of light, which is, I have forgotten, 300,000 kilometers per second, whatever. In 1 second, light goes around the earth 7.5 times. Right? So c delta t is called the time distance. When you multiply c into time, you get the distance. We always measure distance in time. You say, it's only 5 minutes to Vidhan Sauda. What does it mean? The velocity of your walking or your driving. But on the other hand, if you have a traffic jam, your velocity is 0. Therefore, the distance will also be 0. But let's not worry about the traffic jams, which you worry about all the time in Bangalore anyway. So c squared delta t squared is the time distance, but it comes with a negative sign. That is the most important. So when you do this, without going into details, he showed, last time we talked about inertial observers moving with constant velocity with each other, and Einstein showed independently of Lorentz, they have to be transformed using Lorentz transformations. So these, Minkowski showed this, what he called line element is this delta S squared, is independent invariant under Lorentz transformation. Therefore already, since Lorentz transformations preserved Maxwell's equations, the invariance of Maxwell's equations are already built into this. The constancy of light is built into it. And Minkowski, in his seminal paper, he shows that from this simple line element, one line, that's all, and you can show that the lengths are contracted and the time is dilated and so on and so forth. A classic paper. So that he showed, and the space-time came into existence, and this Einstein was going to use into with great effect in his general theory of relativity. That was a very important step because he did, but unfortunately, he did not live to see the fruits of his own great research. Now we go back, okay, we don't go back, we stay there. The Minkowski flat spacetime. Why is it called flat? In a flat sheet of paper like this, I can cover it with Cartesian coordinates, x, y, z. On a sphere, you can't do that. You have polar coordinates. But here, covered by Cartesian coordinates, and line element, which we saw, involves squares of coordinates. That also happens in flat spacetime, only when you use x, y. And four-dimensional geodesics are straight lines. You see that bullet which is going there, it's not accelerated, it's going with constant velocity. So constant velocity lines one can show are four-dimensional geodesics. What is a geodesic? You all know, right? The shortest distance between 2 points. That is in ordinary space. But a geodesic in 4 dimensions is when you have this four-dimensional trajectories, which are also straight lines, because you have x equal to vt or something like that, x naught plus vt, which you learn in high school. They are all straight lines, and also they happen to be geodesic, four-dimensional geodesics. So there is analogy between three-dimensional or two-dimensional flat space like this surface and the four-dimensional space of Minkowski. So that's Minkowski's flat space-time. Remember, we have no gravitation. If there was gravitation, the bullet have gone like that. It might not have hit the bottle at all. It might have hit somebody else who was drinking the bottle. So we have flat space-time, and Einstein will soon enough in this talk. It took him 7 years, but in this talk it will take 15 minutes. He is going to introduce gravitation into that. Before we do that, we have to go back by centuries. This Aristotle, a great philosopher, student of Plato, and he were talking to each other and so on. These were Greeks, ancient Greeks. They believed in something, namely that every truth can be obtained by just reason, by just thinking. You don't have to go do anything at all. But by thinking and thinking, you can come to some conclusion about nature. That's what they believed, and to a great extent that was true. But they could go wrong also. Anybody could go. So Bertrand Russell had this to say. Aristotle could have avoided the mistake of thinking that women have fewer teeth than men by the simple device of asking Mrs. Aristotle to open her mouth. This is crazy. No husband would take the risk of his finger being bitten off by counting the teeth of his own wife. It works vice versa also. If the wife wants to count, she won't take any such risks. But this was the philosophy. You can come to any conclusion by just thinking. And many of the things he said were taken, as we say, Vedavakya in our own culture. Everybody believed what he said. One of the things he said, among other things, that heavier objects fall faster than lighter objects. That was believed for a long time, until this gentleman came in the scene. Galileo Galilei, that is, and my friend and colleague Madhurna has pointed out, asking me to point out to you, look at the date of his birth, February 15th, that is today's date. So, very auspicious day. Some planetary conjunction must have been there. Where is Dr. Shailaja? She knows. Okay, I don't know. So exactly 451 years ago, I did the arithmetic, correct? 451 years ago, Galileo was born, and it is said that Galileo went up the Tower of Pisa and dropped two objects, one heavier than the other, and they both fell down at the same time. And he verified that all objects fall with the same acceleration. But there are historians of science who go into in great detail about these facts, and there are also medical historians. And I heard one medical historian say that he couldn't have done this because the date in which he is supposed to have done that, he was quite old. He could not have gone up. When I was 33, I have climbed up Tower of Pisa. And but now if I have to do that, I don't think I can do. And there is no elevators or lifts there. So he might not have gone. Also, this medical historian said there is evidence, I don't know what evidence, that Galileo was suffering from double hernia. And he had to wear belts. And it was very excruciating. He couldn't have done that. So probably he didn't do that. He need not have done that. Many of the experiments he did was by diluting gravity, by rolling things along the inclined plane. If you go to Florence, there is a museum, Galileo Museum, where they have preserved his inclined plane. So he might have done that. But even there is also, people think, even that he need not have done. He could have done, once again, it's a Grecian, probably the methodology, by just a logic. If one object falls, heavier object falls faster, and the lighter one slower, and suddenly when they get together, what will happen? Will they suddenly know that they have to come with a higher velocity, or will it come with a average acceleration? Nobody knows. So he said the simplest thing is to assume they fall with the same acceleration. So whatever method he followed, he arrived at the fact that they fall with the same acceleration. A fantastic object, it is all great ideas are simple. That's what Tolstoy says. If you read War and Peace, you should read all these things. Einstein used to read. You should also read, otherwise your mind does not expand. So all great ideas are simple. Fortunately, all simple ideas are not great, because otherwise there would have been so many great ideas. What do we do with them? So there is this beautiful quotation. Here is the inclined plane. Go to Florence and look at it. See how beautiful it is. And there is a beautiful quotation here, and I am going to show it to you. Beautifully done by Mansudana. See, coming down. What does it say? Newtonian physics descended from heaven to earth along the inclined plane of Galilee. Isn't that beautiful? That was said by Henry Bergson, French philosopher. I can't help repeating this. There you are. There, Henry Bergson. So, Newtonian physics descended from heaven, by heaven, because it was always, even Aristotle said, the heavenly laws of physics are different from the earthly laws of nature. So, but Newton showed that this moon goes around the earth because of the gravitation, which is also responsible for the apple falling down on the earth. There were the heavenly things, the earthly things, he brought it down. That's what Galileo and Newton did, and here is the great man. Isaac Newton was born in the year Galileo died. So there may be, in India they would have said this Punarjanma, okay, all those things. Probably it's not. And by the way, when the year Galileo was born, Michelangelo died. But Michelangelo died a few days later. So there could not have been migration of souls. So now, so what did he do? The most important thing for us, as we shall see, he showed he gave, as we must have discussed last time, 3 laws of motion, and 1 law of gravitation. With those 4 laws, he could explain everything that was known in his time. Motion of the moon around the earth, motion of the planets around the sun, comets, tides. Even Galileo had made a mistake, but he gave the correct explanation. Not only that, the shape of the earth, nobody had thought of that. All that Newton had done. And when you combine, what is the gravitational force? Gmm by r squared. You all remember? Right. And that is equal to ma. We do that and cancel little m, so that everything falls. But remember, gravitational force law, the m, you should have a subscript mg for gravitational mass. And for ma, you should have I as the inertial mass, subscript I. Why should the two be the same? But nature has done it such that mg equal to mi. That's called a weak equivalence principle. Why weak? We will see the strong one later on. So mi equal to mg, so you can cancel. So whatever the object, the acceleration is the same. Acceleration due to gravity is the same. Everything falls with the same acceleration. That's what Galileo had shown, and that's a very important thing. For example, if you have charges in an electric field, they don't accelerate with the same thing. It depends upon the charge to mass ratio, which happens to be in the gravitational case 1. E is actually the gravitational mass and so on. So because of that, everything falls at the same acceleration, and this became a powerful tool in the hands of whom? Albert Einstein. All right? Now, Albert Einstein says, when in 1907 I was working on a comprehensive paper on the special theory of relativity, there occurred the happiest thought of my life, that for an observer falling freely from the roof of a house, there exists no gravitational field. If a man is falling from a roof, I don't think he will be observing anything. But here is a cartoon, so he is falling and he is trying to weigh himself. You won't find your weight at all, because the weight is shown by the reaction, and there won't be any reaction. He says, that is my happiest thought too, since I will be weightless. So if you want to be weightless, you go into don't fall from the roof. That's called a Gedanken experiment. This is what Einstein was very good at it. Gedanken means thought, thought experiment. So there is something called Gedanken research. What is Gedanken research? It starts in thought, goes through thought, ends in thought, has no relation to reality. So some people do that kind of research also. Not us. Some people do that. Okay. So Pashupati was worried a little bit. All right. So this is what he said, and this became a very powerful tool in his hand, and this is what he said. Again, this is a Gedanken experiment. This is called the Einstein elevator. Actually, it's called the Einstein elevator. You take an elevator and cut off the shaft and it falls freely. Then what happens? As he said, there is no gravity for him. See, Einstein is floating. His pipe and the matchbox and the paper, pencil, everything is falling freely. No gravity. So in Minkowski's space-time, what did you say? When there is no gravity, the space-time is flat. So there is a little bit, a tiny weeny gravity inside the elevator, space-time which is flat. Remember that. No gravity, space-time is flat, everything falls freely. So therefore, what have we done with an accent? See, I am very patriotic. There is India below, which won apparently the match today. No Pakistan there. That was not intentional. Okay. So there is a flat space-time inside and it's falling freely. So with an accelerated frame, this is an accelerated frame because it's accelerating freely, we have annulled gravitation. But by the same token, can we create gravity? Yes, we can. Oh, in Einstein's time there were no rockets, but our chairman is Professor U.R. Rao. If you go and request him, maybe he will send you in a rocket. You can do this experiment, drop 2 apples. If it is going up with gravitational, the same acceleration as you come down, you will find gravity because the floor is moving towards you, therefore it falls with the acceleration and you think there is gravity. So gravity has been created. Once again, as you can see below, there is Earth and there is India. So this is ISRO doing this with Einstein inside. So you can do that. Therefore, by going into a suitable accelerated frame, you can either annul gravity or create gravity. So gravity is equivalent to acceleration. So one-to-one correspondence, you can say it is. So what? For us it would have been so what? We wouldn't even have thought of that. But Einstein thought about it and then he said, let us do this. So he said equivalence principle. I said there was a weak equivalence principle. Mi equal to mg and therefore everything fell at the same acceleration. So equivalence principle of Einstein, which is called sometimes the strong equivalence principle, is this. I have to click once more. Gravitation equals acceleration. That is the strong gravitation. Look at it, meditate, and remember while I energize myself. So gravitation is acceleration. That means what he said was, whatever you see in an accelerated frame, you will see exactly the same in an equivalent gravitational frame. So once again, he thought of this Gedanken experiment. This is taken from George Gamour's book, little book, beautiful book, Gravity or Gravitation. So if you shine light, usually it goes in a straight line. You agree? But then you do the rocket as we did, and let it accelerate. What happens? You have photographic plates here. First it hits at one point. By the time it hits the second one, it would have accelerated. The rocket would have accelerated. It hits at a lower point, again lower point. Then you come down to Earth, and then you develop the films. You see that it had bent. So if acceleration is equal to gravitation, Einstein said in a gravitational field, light should bend. Fantastic conclusion, all Gedanken. But we must give credit to the father of them all. Who was that? Isaac Newton. He wrote this monumental volume, Principia. Probably it's the greatest book in science ever written, and it will be perhaps the greatest book in science ever written for all times to come. But he also wrote a book, Optics. In that there is a queries, about 33 queries at the end. The first query is, will light bend in a gravitational field? Because he had thought of a corpuscular theory of light. If light is made up of particles, it should bend. But of course, Einstein had a completely different theory, completely different formulation, and this is what he said. And immediately, not yet general relativity, He is using Newtonian gravity and equivalence principle, and he computed if you have the sun and there is a star and you see the starlight coming near the sun, how much should it bend? This was done on Newtonian physics. Here is a light particle falling, bending. It's a black light particle. So it's probably ultraviolet or infrared, not visible. But anyway, Einstein himself calculated and gave 0.83 seconds of arc. It's not inches, seconds of arc, and which is an extremely small quantity. And Einstein, it was not beyond him, had made an arithmetic error there, which would have been 0.875. No computers in those days, not even slide rule, not even log tables. 0.83 he got, and then what did he do? Immediately he wanted it to test. So he asked this German astronomer, Erwin Finlay Freundlich, to go and test it. How do you do that? You don't see stars, you have to look at the stars, right? So how do you look at the star with the grazing with the sun, the starlight grazing the sun? You can do it during the total solar eclipse when the stars become visible. You take a photograph of that, you will see the star as it appears, but really the star is there. From the almanac you can get the stellar real position, and then you can find the bending. So 0.83 seconds of arc, and Erwin Finlay Freundlich, he wanted to go, and there was a total solar eclipse in Russia. So poor man went with his camera, crew and all that, but what happened? First World War broke out. When the World War is going to happen, who is going to allow an astronomer to take photographs? So he had to come back with he saved all the films, photographic plates, he came back empty-handed. So Einstein was very disappointed because it was not verified. So he wrote to this great astronomer in United States, George Hale, whether that can be done in broad daylight. And George Hale wrote back, this is called optimism. George Hale wrote back, sorry, Professor Einstein, it cannot be done. See, this is a blessing in disguise. Once Winston Churchill, when he lost his election, he said it was a blessing in disguise, but most effectively disguised at the time. Same thing happened. It was a blessing in disguise, but Einstein did not realize that. Because later on, as we shall see, if he had given 0.83 was not verified, then things would have changed. And Einstein's general relativity probably would not have been hailed as the greatest theory ever. Okay, now this is what happened. But you see, when this was early 1908, it is 1907, that's when he did the calculations after his happy thought. But then there was a gestation period. Always, the Einstein was well known for his gestation period. Even as a child of 3 years, apparently he did not, until the age of 3, they say, he did not talk. Because probably when other people talked without thinking, he used to think without talking, even as a child. So they say gestation period, where he did not really come out and say, I am thinking about this. But suddenly he would tell you what he had thought. That's what happened with special relativity. Recently a historian wrote to me raising this question. He took a walk in May to see Bessot, his friend, and discussed about time, and he said, it came to me that time was suspect. So as soon as he realized time has to be modified, within 6 weeks he wrote the paper. But for those 6 weeks, there was a lot of gestation period, and there was gestation period for this also. And so it started falling. Okay, let us go back. What happened? Yeah. So we said there are Einstein elevators, and in each there is a little bit of flat space, right? Flat space time. But all over there are different elevators, different little pieces of flat space time. So if you put them all together, it can add up a curved space time. See, you can have little flat space. If you put them all in a flat one, you won't have gravitation at all. You don't want to do that. You want to put it together, flats, so that you can get a curved space time. Einstein must have thought like this, because when he gave the final theory, he talked about local flatness. So, but we are reversing a little bit, taking liberty. I'm sure he must have thought of all these things, nothing new here. So the same thing happens here. It falls, okay, and all these fall, and the different little space, flat space time, and this is the two-dimensional analogy. Here is Einstein, flat, 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 flat. This is how BDA will sell you, or anybody will sell you, the plots. They're all flat, they don't say curved. but when you put it all together, you get a curved space. So you see, it's a two-dimensional analogy because although we live in four-dimensional space-time, our awareness is confined to three, our imagination to two, and our viewpoints to only one. So anyway, this is the two-dimensional analogy. Therefore, we have curved space-time, and Einstein was going to introduce his curved space-time. But this is not the only way he came to the conclusion that space-time should be curved. So you can watch that. This is not being streamed, fortunately, this drinking business. So he made a geodesic hypothesis. He made it actually. What he said was, if you have curved space-time, the geodesics, the shortest path, should also be curved. Or vice versa, if the paths are curved, space-time in which they are embedded must be curved. Before he came to that conclusion, this is called the missing link. What's the missing link? He said acceleration is gravitation, right? And here is an accelerated frame, which is a rotating disk, as you can see in Tompkins and Wonderland picture. And these people are actually marking the geodesics. They are not straight lines, they are curved. And if you add all the angles, alpha, beta, gamma, it will be less than 180 degrees. If it was flat, it would be 180 degrees. Less than 180 degrees means negative curvature. And also you can see some people are measuring the circumference and the radius, and it so happens the ratio will not be 2 pi. Einstein actually didn't to look at the geodesics, but looked at that, and he did not publish it. So this is called the missing link in Einstein's general theory of relativity. So we have for you, here is a video, and either Srinivas, our friend here, or Madhusudan, I can't tell from those pants there. Let us see what happens. You have this rotating platform outside. We built it so that people can do this experiment, but now children use it as a merry-go-round. So it's not rotating. See? Straight line. Poor man is doing again and again and again, he will get tired. So let's go to the next one. Starts rotating now. What happened? It's not rotating. Ah, okay, it sat down. All right. See, rotating. And where it is going? Going that way. Remember, going that way. All right. Now, what is he going to do? It's going to rotate still. See, this way. It's going that way. And if we had another here, you would have found the same thing as in the picture. All of them like this. And I said, it's negative curvature. Okay? This is how it is. On a flat space, these two are parallel lines. It need not be parallel. Okay, parallel lines. We have taken geodesics. And here it is like that. In the negative curvature, it's like that. And remember, there are beetles going, because beetles want to go in the shortest path. Very intelligent beetles. But we don't do this. Sometimes you go to friend's house and the older people go to the nearest bar and so on. So Einstein made this hypothesis, geodesic hypothesis. I already told you the natural trajectories of particles moving in a space-time are geodesics. In flat space-time, they are straight lines. Their curvature indicates the curvature of the space-time they are embedded in. So if you have gravitation, if I throw something, it goes in a curve. But even if you drop it, in 3D it is straight line. But if you plot it in time, it is S equal to ut plus half at square. You get a parabola, which is a curved geodesic, and it tells you the space is curved. So therefore, we have a curved space-time. That is the essence of the geodesics. Okay? So I hope I have got you. So hypothesis, and we have here a cartoon. Geodesic hypothesis. In a crooked world, the straightest path is also crooked. Politicians know this geodesic hypothesis. Here a crook is going from bank, takes the shortest path, doesn't know it is going to jail. So you can say this is a denotification of the revenue land, and here is the Lokayukta, and the final destination is the same. So that is the geodesic hypothesis. And so one more representation of this to give you the essence of general relativity. And here is an acrobat net as in the circus. And you can see there are two acrobats. The one on the left is grinning and standing there. Poor fellow here is trying to jump. But here the net, there is nothing there. It is flat. You can have Cartesian coordinates. So that is the flat space-time of Minkowski. See, now what happens? The acrobat has fallen. There is a bigger grin there. And there is gravitating matter. There is curvature of space-time. But far away from the mass, it is still flat. It's called asymptotic flatness. And you can have Cartesian coordinates. But there is a dimple there. So if you roll a ball, it will fall down. Newton would have said there is a gravitational force. But Einstein says it's a geodesic. So it has to go there. And if the mass keeps on increasing, things cannot come out. And that's called, what is it called? A black hole. Everybody knows. And you can go up and down, and there will be ripples in the space-time, and it's called gravitational waves. We'll talk about it in the next talk. And all this can happen in this net. So all right, you have all this. I have told you these ideas. Einstein had all the ideas. He knew curvature space-time has to be curved. So the general theory has to be of the curved space-time. But where is the mathematics? He did not go to his mathematics classes. So he went to Grossman, Marshall Grossman, his classmate in the Poly. He was a brilliant mathematician too, and he did attend Minkowski's classes. Not only that, he took down notes. And Einstein borrowed his notes so that he could pass. When I was in high school, I used to borrow notes. I didn't cut classes because attendance was there. But I didn't take notes. My friend took very good notes. I used to borrow. I stopped because one day suddenly he said he was going to charge me for giving it. I said, no money, I will take down my notes. But Einstein didn't do that. He used to borrow that. And so he went to Marshall Grossman, what should I do now? How do I formulate my theory? Grossman said, don't worry, Einstein. There was this great mathematician, geometer Riemann. He had done it all, not general theory of relativity. The Riemannian geometry, which talked about metric, curvature of space-time and everything, you use that and you will get the mathematics right. So Einstein worked for 7 years. Well, more than that probably. Anyway, from special relativity to general theory, there were 10 years. And in those 10 years, he formulated the theory, he gave the equation, everything was done. And the fantastic theory came out. And so, when he gave the theory, we don't even know what the next one is. So, here is the evolution of general theory of relativity in his own words. In his own words. He says, I am now working, this is about general relativity, he wrote to his friend, it was named Habicht. I am now working exclusively on the gravitation problem. Compared with this problem, the original theory of relativity is child's play. That's how difficult it was. The next one, it's going on, it's going nearer and nearer. He says, nature is showing only the tail of the lion, but I have no doubt that lion belongs to it, belongs to the tail, even though because of its large size, it cannot totally reveal itself all at once. So the lion did not reveal itself all at once. Slowly it revealed itself, and finally he had the lion by the tail and the mane and the ears, everything. So finally when he had it, he said, the theory is beautiful beyond comparison. Hardly anyone who truly understands it will be able to escape the charm of this theory. It was not empty bragging at all. It was not bragging. He was telling the simple truth, as everybody accepted. This is what Newton did too. When you read Principia, there are first two books, or 2 parts. After he has done the mathematics, physics, the third part is called the system of the world. And he says, I have demonstrated to you, shown to you, the mathematics of all this. And with the same mathematical theorems, I will now demonstrate the system of the world. Again, not boast. That's what it does. And that's what he did. Okay? So, the theory was there. He gave the theory. And the hardest part was to give the equations And here are the equations. Einstein writing the equation Rik equal to 0. Some of us have been making our living writing this equation, even if we do not understand this completely. We do understand somewhat. Okay, I wrote an article about Chandrasekhar, the legendary great astronomer, astrophysicist. He came here and saw our first program, and that afterwards he gave me the greatest compliment I have ever received. He said, Vishu, that's my nickname, it's beyond my comprehension how someone who makes a living looking at Einstein's relativistic equation can produce a program that is so beautiful. Anyway, I hope the first program will be brought back, so I can not boast, but I will also say system of the world. Anyway, these equations, actually Rik equal to 0, it's a very shorthand form for 10 nonlinear equations. Nonlinear means, see, if you take Newton's equation, not GMA by R square, but the equivalent of this is del squared phi equal to 0. That's for empty space. This is for vacuum. So phi is one gravitational potential, one linear equation, easy to solve. But here non-linear equations, 10 variables, all mixed up. It's extremely difficult to do that. Next talk I will be talking about the simplest case in which it was solved for the black hole. But if you don't have 0 on the right hand side, you will have to put in a tensor, this is a tensor, which tells you about the energy, momentum, mass and all that, which makes it even more complicated. And that's what he is writing, and that's what the equations were. With that, he could prove a number of theorems. Here is once again Matsudana found this. Space-time is curved through Einstein's picture. So, the first application, it's called the 3 classical tests of relativity. This is the precession of the orbit of Mercury. See, the Mercury's orbit doesn't close simply, but each time it precesses. Look at the perihelion, that's the point closest to the sun. It's slightly moving. How much is it? The precession of Mercury orbit is measured to be 5,600 seconds of arc per century. Newton's theory of gravitation, taking into account all the effects of the other planets and so on, predicts a precession of 5,557 seconds. But there is a discrepancy of 43 seconds of arc. Einstein, without probably knowing this, calculated it, and what did he get? Exactly 43 seconds of arc. When he did that, he was so excited, so exhilarated, so exhausted. For 3 days, he could not do any work at all. Something unknown in his life. And then he immediately, the other effect he also predicted was light when it is emitted from a strong gravitational field to a lower gravitational field will be redshifted. Not so much. Blue won't become red. It's also very minute quantity. In the spectrum of the stars, it was verified, but even terrestrially, it was much later verified also. And finally, there is also the light bending. You remember, way back in 1908, he had calculated and got 8.83 seconds of arc. Now, see that light, now it has become white. It's falling down, and that is heralded by the sound here. That happened to be only 1.75 of arc. How much did he get earlier? But it should have been exactly half of that, 0.875. This is what he got now. Now I told you that it was a blessing in disguise. If they had found 0.85 and then he had given general relativity, somebody would have said, wow, he fudged everything, got a new theory to get this. No, he forgot about this, he gave a new theory and predicted it, and it was verified by Arthur Eddington. He also comes in the story of Chandrasekhar, as some of you know, but he predicted in a total solar eclipse in a small island off the coast of Africa called Principe, or Principe, I don't know. And on the right hand side is the plaque to commemorate that thing. And when this happened, J.J. Thomson, I showed you this. This is the most important result related to the theory of gravitation since the days of Newton. This result is among the greatest achievements of human thought. This result is actually general relativity. So immediately what did Einstein do? As a good son, he wrote a letter to his mother. Dear mother, today I have some happy news. H.A. Lawrence telegraphed me that the English expedition led by Arthur Eddington have really verified the deflection of light by the sun. When this happened, overnight Einstein became world famous. Not only world famous physicist, but probably the most famous person in the whole world. And when this happened, he also made a rather startling statement that the great Max Planck, he said Einstein, I think Max Planck, I think Einstein thought that Max Planck did not know enough physics. Einstein had great reverence for Max Planck. How can he say? Because he said, when Eddington was going to verify or not verify Einstein's prediction, Planck could not sleep at all. And Einstein said, I had a very nice sleep, whereas Planck spent a sleepless night because he did not have enough faith in the theory. And that's what happened when a doctoral student, Ilsa Rosenthal Schneider, and asked Einstein but how he would have reacted if his general theory of relativity had not been confirmed experimentally that year by Arthur Eddington. Well, did he say, I would have been disappointed? And did he say, I would have gone back and created another theory? No. What did he say? This is what he had to say. Then I would feel sorry for the Lord. The theory is correct anyway. The theory was correct. If the Lord did not implement it in nature, Einstein would have felt sorry. But God in his infinite wisdom had implemented it, and it was verified, and the theory was correct. And since then it has been verified by innumerable methods. I don't know why you have to verify. There are so many things that have happened. So it is a fully established theory. And so finally, so I have given you some flavor of general relativity, I hope. Finally, to sum it all, later on, his son, Edward, he had two sons, Edward, who became an engineer, and Hans Albert, unfortunately, he had psychological problems. He had to end his days in a mental asylum, very unfortunate story. But Edward asked him, why did you become so famous? So Albert Einstein said, when a blind beetle crawls over the surface of a curved branch, it doesn't notice the track it has covered in the indeed curved. I was lucky enough to notice what the beetle didn't notice. This was precisely the geodesic hypothesis which laid the heart of general theory of relativity. If you have a curved space-time, so are the geodesics. If the geodesics are curved, space-time is curved, and you have general theory of relativity. So here is Einstein in 1916 had become a watchword in every household. He had become overnight completely famous. Now you see, he has all the files neatly arranged. His hair, Professor Einstein, his hair is combed neatly. It's not the same image we have of unruly hair flying in the air and a floppy sweatshirt, baggy pants, scuffed shoes without socks. That's how Einstein was towards the end. Look at the shoes, highly polished. And look at the cardigan, everything, naturally dressed, and posing with one arm like that. So finally, the great Paul Dirac had summed up general theory of relativity. If the special theory hadn't been discovered by Einstein, it would have been discovered within 3 or 4 years by one of 3 different people. The 3 candidates he had in mind one was Lorentz, who had given the Lorentz transformation. Second was Poincaré, had come very close to Einstein's theory of relativity. The other was Larmor. He was also thinking along the same line. On the other hand, the theory was in the air. On the other hand, if the general theory had been created by Einstein, then it probably wouldn't have been invented to this day. To this day and probably never. If so, no black holes, no gravitational waves, and no theoretical basis for cosmology. And these are the 3 things I will be talking about when I am going to talk about theory of relativity next time. Before I conclude, my popular demand means the behest of my friend and colleague Madhusudana. He says I have to go back 3 centuries before Newton and go back in history to one Gurutvananda. This is research into ancient Indian legacy. Apparently, this Sri Sri Gurutvananda. I don't know how many Sris you can add. Some people, Swamiji says Sris also. Somebody, Sri Sri Ravi Shankar. Maybe he had n number of them. I don't know. Anyway, this Gurutvananda apparently had discovered Newtonian gravity 300 before Newton, and he gave it in Sanskrit. I should refresh my memory about Gurutvananda. Where did it go? I don't have it. I will read it from here. Okay. He said, Balam nam GMM ityastha or square ityaten bhagaha. I will translate it for those who do not know Sanskrit, including myself. Okay? I don't know Sanskrit. Force is Gm, one m is big, the other is small. He was very careful. Gmm divided by r square. But you see, when Newton discovered it, there were a lot of apple trees. In his own house, there was apple tree, and Stuckley, who was a medical doctor, his friend, he was the first biographer. He says, Newton and Stuckley sat after tea in the garden, and there was the apple tree, and Newton said, this is exactly how he has sat there, and the apple fell, and he thought, not on his head, as many stories say. Maybe it fell on his head, maybe. And actually, there is a whole story. You will read in the Jawaharlal Planetarium is putting out one newsletter called Baseline. Read in the next one the article I have written about this. So it might have fallen on the head. Anyway, there were in his own orchard, in his own backyard, there was an apple tree. But this was Gurutvananda belonged to South India. Hopefully, Karnataka, Mysore state. And Keralites may say Kerala. Anyway, but there are no apple trees as far as I know. There was a lot of coconut trees. So he sat beneath the coconut tree, and in case of Newton, the law of gravitation was discovered by the fall of an apple. But here, it was discovered by the fall of a coconut. The last moment has not been videoed because it's a selfie. So the last moment was not recorded. Let me show you the whole episode if you have missed it. So this was the first case of authentic case in unrecorded history of perishing without publishing. Thank you very much.
First of all, we would like to thank Professor C.V. Vishveshwara for this very insightful and brilliant talk. Insightful on two counts. One, for providing insight into this wonderful but a very difficult subject. And second, for inciting all of us to read more about the subject and derive pleasure at a higher level. Thank you very much, sir. Then we would like to thank Messrs. Video Hut Productions, who have not only made the video coverage possible, but have made all the arrangements for the live streaming on our website. And in addition to hundreds here, thousands would have enjoyed the talk elsewhere. So thanks to Mrs. Video Hut Productions. And finally, we would like to thank all of you, the audience, who have, I'm sure, will participate in a very interactive manner after this vote of thanks for your questions. And so thank you very much for your presence. And finally, we end with the announcement that the next time the final talk in the series will be held on the 8th of March, second Sunday of March, which happens to be a couple of days after the birthday of Michelangelo, which I mentioned. So we hope to meet you again. Thank you very much.